Hello, everyone. Let's get started. My name is Daniela Roos. I'm the director of MIT's Computer Science and Artificial Intelligence Laboratory, and I'm delighted to welcome you this evening, to the Dertouzos Lecture Series, and especially excited to introduce our guest, Bob Metcalfe. Bob Metcalfe, an MIT engineer and graduate, Ethernet inventor, Xerox scientist, 3Com founder, retired professor of Stanford University and UT Austin, and CSAIL researcher now, or the way he likes to put it, CSAIL postdoc. Now, if you've ever connected a computer or to the network, you can thank Bob. He revolutionized how we communicate by creating the Ethernet while at Xerox PARC in 1973. Now, at that time, he was tasked with devising a plan to seamlessly connect the company's new personal computers to each other. But as a result, he helped pioneer the internet. Now, later on, he founded the company 3Com, which stood for Computer, Communication, and Compatibility. 3Com manufactured internet hardware and software, including the first Ethernet for PCs. And Bob worked tirelessly to push his invention as the standard for local area networks. Now, Bob's first love before the Ethernet was ARPANET. His first job at his alma mater, MIT, was constructing hardware to link MIT to the ARPANET, which he fitted with a comprehensive pamphlet on resources and tips for usage. While at MIT, Bob earned degrees in electrical engineering and business management. He then earned a master's degree in applied mathematics from Harvard and later completed a PhD in computer science at Harvard as well, but rumor has it he was mostly at MIT during his PhD studies. Now, Bob loves to make predictions, like his famous pronouncement that the internet would go spectacularly supernova and in 1996 it would catastrophically collapse. But when that prediction failed to come true, Bob, in front of an audience, put that particular written column into a blender, poured water over it, and proceeded to eat the resulting frappe with a spoon. Our former lab director, Michael Dertouzos, said his shenanigans, like eating his own column, are marvelous shenanigans. So Bob is a life trustee emeritus of MIT and a member of the National Academy of Engineering. He received the IEEE Medal of Honor in 1996 and the National Medal of Technology in 2005, both for his leadership in the invention, standardization, and commercialization of Ethernet. And in 2022, he also received the Turing Award, the highest honor anyone can get in the field of computing. Before I pass it to Bob, I'd like to invite you to mute your phones and feel free to put your hands up if you have a question during his talk. We will also take questions at the end of his presentation. And so now let's give Bob a very warm CSAIL welcome.
I'm going to begin by giving you a reverse preview of all my slides. This is accidental, by the way. But that's what it's going to be. I can't wait. Okay. I'd like to convince you all that connectivity is a thing. It's the thing. I have found it to be the way to enter any situation is by looking at its connectivity. And if you're building something, figuring out how to build the connectivity. Hence, that phrase is the thing. I also believe that the most important new fact about, facing the human race is that we are now all suddenly connected. And by suddenly, I mean the first packets were switched on October 29th, 1969. So in that time, we have signed up 5 billion people to be users of the internet, which is about 2/3 of the human race. Now, Going back, I was born in 1946, and that's my baby picture. Look what my mom put in my hands. What was she thinking? That thing there. So, but the cool thing about being born in 1946 is 1947. And there we had wireless television began its commercial ramp, and famously was invented the transistor. And the transistor has basically driven all the connectivity I've enjoyed since 1947. Now, of course, roads are a form of connectivity, and of course the Chinese have a saying about roads also, and there it is. If you want to get rich, build a road. Connectivity is key to creating value. The Romans also were fond of roads. This is a subway map of the Roman Empire. And then there was my ancestor, blind Jack Metcalfe, who had a road technology here, which he used to build the first 180 miles of road leading England into the Industrial Revolution. So I'm going to tell you some stories now, but your goal is to be, at the end, is to be able to know the difference between ARPANET, ALOANET, Ethernet, Internet, and Wi-Fi. They're all different, but they're all, of course, connectivities, technologies. Here's how bad things were. My mom, when I'm getting in the car to drive from New York to Boston to attend MIT, she said that. Bob, when you get there, Bobby, when you get there, give us a call, but let it ring 3 times, then hang up. Many of you remember that. My mother loved me, but not that much. And the AT&T monopoly was sitting on top of connectivity at that time, but this was their product introduction in 1950, the Model 500 telephone, and this was their product introduction in 1984, the Model 500 telephone. Do you notice differences between these two? Demonstrating the difficulty of monopoly on, in this case, on connectivity. And then this was my personal computer in Sudbury, Massachusetts at the Raytheon Corporation, an IBM product. This was the modus operandi. In the beginning of the internet, this is how computing was done in the real world. People punched cards, made decks, submitted the decks overnight, received their error messages printed out in the morning. And this was my Fortune 01 out in Sudbury. And so while we were beginning to build the internet, there was a new wave of computing coming, interactive time sharing. And here's a picture of 2 PDP-10s, my favorite machine. And then the way you access a PDP-10, of course, is through a Model 33 teletype. So this was the wave. This was the new wave for which the ARPANET, the first generation internet, was built. It was built to connect those machines. DARPA was tired of buying a PDP-10 for each of its PIs. So they wanted, Bob Taylor sat in his office there at ARPA, and he had 3 terminals to connect to 3 PDP-10s. And he wondered, why do I need 3 terminals? So he funded the development of the ARPANET. So there we had the first version of the internet, called the ARPANET, and it was based on a protocol called Telnet for a purpose. The purpose of the ARPANET was resource sharing, unquote, and the protocol, by resource sharing, they meant logging into somebody else's PDP-10 so that ARPA didn't have to buy another one. And so we developed the Telnet protocol over there on the 9th floor of Tech Square. And this allowed us to log into machines around the world. And the first login occurred here. This is the date of the first login at UCLA. And they typed L, they were going to type login. So they typed L, and they typed O, and then the machine crashed. But they managed to fix it, and the rest is history. Now, while that's all going on, I'm being mentored by MIT people. And I just, more than this, but Jay Forrester over at Sloan was teaching me feedback loops in complicated simulations. Don Troxel was teaching me how to use 14-pin dips from the Texas Instrument catalog. Marvin Minsky was my undergraduate thesis advisor. And the thesis that I wrote for him, I just recently remembered, was entitled A Neuron Model and Some of Its Information Processing Capabilities. All copies of this dissertation have been lost. Minsky didn't like it. I don't think he thought I was smart enough to do AI. So he sent me down the corridor to do networking instead, on the 9th floor of Tech Square. Now, Butler Lamson wasn't an MIT professor then, but he's an MIT professor now, and he was my mentor at Xerox Research. And then Mike Dertouzos hosted me in 1970. I spent a year here in 1979, and he helped me start my company, 3Com. And that was going on while we were networking terminals. Lick isn't on the list. I'm sorry. So, if the only tool you have is a hammer, as you know, everything looks like a nail. My hammer is connectivity. And in case you're wondering what connectivity is, it's the stuff that you use to move, the apparatus you use to move stuff from A to B, including, mass and energy, or what the internet is moving signals from A to B. It's odd how I got into this business. I took a series of electrical engineering courses, 601, 602, 6001, 670, 6711, 6721, and the last was a project to build an acoustic delay line memory. So I built it and graduated. And basically, an acoustic delay line memory is a packet full of bits that you send down a cable, and it travels at the speed of sound and comes back out again. So it's sending data from point A to point A. But the purpose of doing that is to remember it, and it'll come back a few milliseconds later. The reason this is so important is that, so I built a machine that would take bits one at a time and send them down a long cable, and that would later become important. Now, by the way, since connectivity is my hammer, I have a joke about it. But the trouble with this joke is it's wearing out. I've been telling it for 4 years, 3-4 years. And so by virtue of having built these connectivity devices, I became a member of the Connectivity Society. And we met quarterly. We still meet quarterly. And our last meeting was really sad, because the inventor of USB had died. So the members carried his coffin across the street to the waiting grave, and we lowered it into the grave, and as we lowered it, it jammed. So we had to pull the coffin out of the grave and rotate it 180 degrees and put it back into the grave. So now you know why this joke is getting old, because the USB's been fixed. And so people are dying off, and this joke is getting less funny every year. Okay, so finally, because I had built this delay line memory, MIT gave me the job of connecting it, one of the people, to connect it to the internet, then called the ARPANET. And so I built this thing. It took me a year, because I was learning the 7400 series of TI at the same time. And so this was my second device that sent bits down a long wire, one at a time. And this is what the internet looked like around then. So I put MIT on the network here, and then I put Xerox Research on the network here. This is the kilobit internet. These circuits are 50 kilobits per second. I like to remind my colleagues at the University of Texas, you'll notice it goes through Texas, but it doesn't stop there. And this network was a resource sharing network, the purpose of which was to enable remote login. So then I appeared at the Xerox Research Center, and where Bob Taylor, who had been the guy who funded the internet initially, became my boss in the computer science lab at Xerox. And let's see, just to make a long story short, I built another interface to connect to the internet, this one for Xerox. And then, let's see, yeah, and this is what it did. These were the terminals accessing the internet. On paper, the ASR 33 teletype, and then a major transition to the glass teletype. So instead of printing on paper, it would print ASCII characters on a glass teletype. And so that network is up and running. Let's see if oh yes. So here I am having twice connected things to the resource sharing internet. And this is me in my office just before Ethernet. So here is a modern Texas Silent 700, Texas Instruments Silent 700, 300 bit per second, 30 characters per second, with an acoustic coupler. You can almost see it there. Here is an actual Rolodex. This is the Model 500 telephone that I have on my desk. These are pencils. And this is the, what's that? Slide ruler. Is it on there somewhere? I had a slide rule, it just wasn't in the picture. And then there's this electric typewriter, which the typewriter was made in Austin, Texas, but I used it to type the memo inventing Ethernet. So the computer science lab decided to build what is arguably the first personal computer, if not that, the first cool personal computer. And we were sitting in a meeting and we said, well, we need a network for these things. Who here knows how to send bits one at a time down a long wire? Me. So I got the job, build this network. And one of our requirements was a page per second laser printer, 500 dots per inch, which required 20 megabits per second, raw. So Dave Boggs and I, he was a grad student at Stanford, may he rest in peace, designed this network that would send packets down a shared coaxial cable, half-inch thick. You could connect two locations by using what later would be called routers, using telephone circuitry. And you could also, we imagined someday, have a network that used radio instead of coax, so we called it the radio ether. This is where I claim to have invented Wi-Fi. It really annoys the actual inventors. So the feature of this network is we used a shared coax and used Gerald taps to puncture that coax if you wanted to install a PC. You just put a drill into it, and that way you could install a PC without bringing the network down. That was our goal. And then we needed to clock the bits. As you put them on the medium, you need to clock them into the shift register at their recipient. So we needed a clock, but we avoided a global centralized clock that needed to be synchronized, and instead we put a clock in every packet. So we used Manchester encoding, which meant that in every bit cell there would be the bit and then the complement of the bit, which guaranteed that there was a transition in the middle of the bit cell, and that was made into the clock the bit into the register. And then I spent a month in Hawaii figuring out how to use the Aloha network, which was a packet radio terminal network. And I learned two things there. One, radio was not practical for a local area network. The semiconductors did not exist. The Aloha network ran at somewhere between 4 and 10 kilobits per second, not megabits, kilobits. But their access method, randomized retransmission, send the packet, gets through, great, doesn't get through, randomize, and try again. And so we decided to adopt that for Ethernet, randomized retransmission. But because we were a coaxial cable, we could do things that the radios couldn't do. So we added carrier sense, don't send anything that clobbers something. Carrier detection, if it does clobber something, notice it. And if there's too many collisions, back off. And so we added those three features. So the first Ethernet was a Gerald Manchester Aloha network for connecting PCs. An Alto is a PC. And let's see, where is the, I've lost track of ears. Anyway, there was a really cool printer called Ears. So then we decided to call this network Ethernet, not coax net, because we anticipated that in the future it would be able to use other media. For example, radio, for example, telephone, for example, optical fibers. And so we debugged it. So this is an Alto with this is a removable, this removable media was 2 megabytes. And then Dave Boggs and I spent half a year huddled around this card. This is the 60-chip card that we use to connect to the Ethernet. And this is the Alto PC with its guts open. And then we entered a competition. You don't think that my colleagues at the Xerox Research Center would let us build a network without any competition? Well, haha. Everybody wants to build a network. First of all, there was SneakerNet, which is a standard competitor to any network. I don't need a network. I can just walk there. We defeated SneakerNet. We invented Command P. You may have heard, you may have typed that one. Parallel ports, the machine had parallel ports. SIGNET was cool. When I arrived there, the SIGNET was being developed by Charles Simonyi. This is Simonyi's infinitely glorious network. And they, Butler et al., kicked Charles off that project, said, you go write a text editor and let Bob build a network. And so he went off and he wrote what became Microsoft Word. And he's the 4th billionaire out of Microsoft. And I got to do the network. Then one of my colleagues noticed that we were having trouble getting the transceivers to work. And he was upset about this because he didn't think I was much of an engineer because I had a Harvard degree. He didn't see the MIT degree. So he decided to build another network to compete with Ethernet called XNet. And eventually we fixed the transceiver thanks to a guy named Tad Lamb. And eventually he gave up on this alternative project, but he was ready. This was a very bad idea. It was a 16-bit parallel network. So it wasn't going very far. And then there was Ethernet, which won, and it won for a bunch of reasons, but the one I like the best is I also had the job of building the operating system and the network protocols for this laser printer. And the only way you could print documents on this laser printer was over Ethernet. So therefore, everybody who had an Alto on this network felt compelled to opt to be on the Ethernet. And that's how we won. We cheated. Later, I worked with Eric Rawson, and we did a 100 megabit per second optical version of Ethernet. And we abandoned it because there was no machine that could take 100 megabits per second. It was just too fast. So there it is, the beautiful Alto with an Ethernet in it. And you can't see the Ethernet because it's cleverly hidden in the back. So then, in 1979, I left Xerox in order to commercialize these internet technologies. I gave Xerox 7 months' notice, and I had no idea what the company would do. But I ran into this guy who called me at my apartment on Beaver Place in the Esplanade. And he was in a recruiting mode, and I was in a selling mode. So I showed up in Cupertino with a presentation that he should buy from me a network called The Orchard. Get it? Apples. That was my current concept of marketing. Steve had no interest whatsoever in Orchard. He was out recruiting, but he didn't get angry with me. He was sympathetic, and he helped me build my company. So he helped me by insisting that I buy an Apple II, and that I buy a thing called VisiCalc, and I run VisiCalc, and there it is back there, to produce a business plan to raise venture capital. And I raised venture capital. This is the swashbuckling entrepreneur. This is the investor, and this is my adult supervision. And we started a company whose goal was to provide the products that underlie the internet. This company, at the end of 1999, inflation adjusted, note that, was worth $70 billion. And it started with my net worth at the time was $27,000. And then a really cool thing happened. Since the Ethernet was designed to network personal computers, it would be helpful if we had some personal computers. And IBM did us the favor of introducing the IBM PC in the fall of '81. And we quickly developed an Ethernet card that could plug into that. And in short order, we were shipping millions of them per month at a price that ranged downward to, say, $100. Now, the Ethernet that we were marketing turned out, well, it was a 10 megabit per second version, but the Gerald technology wasn't used anymore, and the Manchester encoding wasn't used anymore, and the alone-out randomized retransmission wasn't used anymore. So what did Ethernet actually contribute? And there it is. Ethernet brought packets to the desktop. Prior to Ethernet, the packets would go to the host, it would be converted into some application and produce ASCII characters, which would then run down and appear on your glass teletype. And Ethernet brought those packets, internet packets, all the way to the desktop so you could write programs on the desktop that use the network directly. The second thing Ethernet did is it ran at 2.94 megabits per second, which was 10,000 times faster than the network it replaced. And I didn't say 10%. I didn't say 10 times. 10,000 times faster. And so thereafter, the internet was characterized by an abundance of bandwidth and made practical the uploading of cats. And the third thing Ethernet contributed is it joined the movement of standards. The internet was a standards movement. So in addition to IP, TCP, Telnet, FTP, you had Ethernet in this list of standards. So that was the real contribution of Ethernet, which we discovered as we were making and selling it for the marketplace. So while this is going on, the platforms that we were attempting to interconnect changed over time. I mean, as I mentioned, we had card batch processing to begin with, then dumb terminals carrying ASCII characters that migrated from paper to glass, and then eventually had a red ribbon. So you could switch between black and red. That's a hot medium. Workstations, personal computer local area networks, client-server computing, cloud computing, SaaS computing, all of which were platform evolutions. And then we had traffic evolutions. We started with ASCII characters, voice, video, and then the voice, video, data marketplaces began to converge. Voice used to be telephone, video used to be television, and data used to be computing, but over time, those three major industries have converged, or are still. And next we're going to say IoT. Right now, 80% of the traffic on the internet is video. And it was never designed, I was there, it wasn't designed to carry video. Video was a surprise. There's lots of surprises in this story. Here come some more prizes. So there were disruptions, and you're familiar with all these. You know, publishing, advertising, journalism, commerce, all gone, all disrupted by the internet. But now we're approaching an even bigger set of disruptions. What's that?
Politics disruption.
Politics, yes, I'm sorry I left that off. Did I really leave that off? I shouldn't have left that off. I've been advised to avoid politics. With my politics, you avoid politics, yeah. So now we have even bigger disruptions coming. Work, learning, health, energy, transportation, some really big ones. The biggest one of all, the one I'm most interested in, is the reduction of extreme poverty. So this is a really cool graph. It shows the number of people not in poverty and the number of people, extreme poverty, and the number of people in extreme poverty. And you will notice that this curve, which has been growing since 1820, all around here, after the introduction of the internet and just before the introduction of the World Web, this curve starts heading down and down and down. And I know the difference between causality and correlation, but I always think of correlation as a first step toward causality. And so here the internet takes credit for the reduction of global poverty. Now, the advance of connectivity has been sudden. You remember, go all the way back to October '69. And my claim is it's the suddenness that has created some pathologies. Here's a list of some pathologies. The first one was hacking. I wrote a RFC, request for comment, in December of '73, reporting how 2 grad students got somebody's root password and broke into the ARPANET on Christmas Eve in 1973. So hacking has been around for a long time. Then there's pornography. The US government almost shut down the internet because it was so good at carrying pornography. But they even passed a law called the Communications Decency Act. And so there's no more pornography on the internet. And then advertising. Now, what's that?
We struck down the law.
It's been struck down?
Oh, yes.
I'll have to modify the slide then. So advertising became a scourge. Those of us grad students who built the internet were offended when advertising hit us. 2 lawyers in Arizona were prominent in this. But then we discovered.
They weren't being lawyers.
What's that?
They weren't being lawyers when they were doing it.
Oh. Okay. Are you being a lawyer now? Yeah. But we discovered in short order that advertising wasn't a pathology. It was the principal means of paying for the construction and operation of the internet, hence Google, Facebook, et cetera. Now, we are left with a residual amount of advertising called spam, and that's going on. Congestion, the network collapsing now and then. I was wrong about that in 1996. Polarization of tribes on the internet, addiction, loneliness, suicide, censorship. These are all, and fake news is the big one. And my claim is that these will be handled in the fullness of time, like the preceding pathologies. They just need time. We were rushed into this, and we're going to have to figure it out. This is the first paid internet ad, paid in 1994 by AT&T. I apologize for the blurriness. Now, there have also been some serious surprises, and there's 3 of them that I call reversals. So Herb Grosch was an IBM executive, and he had a law, Grosch's law, which said that the cost of a big computer went up as the square root of its power. And the implication of that law is that bigger computers are better. And but at the same time, there was a new law that, this is 1965, this is 1958 or something. There was another law, Moore's law, which is tantamount to saying smaller computers are better, especially if you connect them. And guess who won? Yeah, Grosch lost, Moore won. I'll return to this point in a moment. Nicholas Negroponte, MIT professor, noticed another thing. We call this the Negroponte switch. For a long time, we thought that long-distance communications would be wireless. And in the building, we would use the old copper that AT&T had been putting in for 100 years. Nicholas noticed it was the reverse. So today we carry wireless locally, namely Wi-Fi, and we go long haul through cables, optical fibers typically. So that was a big switch. And then there was another big switch, and Marconi won the Nobel Prize by getting radio to go further and further and further until about 1905. And ever since then, according to Cooper's law, and he has lots of data on this, I'll show you in a minute, progress in radio has been going shorter and shorter distances. So now we're down to 6G, and we have a range of 1,000 feet in order to do frequency reuse and power consumption. So that was another big reversal, surprising reversals. Now the Grosch law reversal had the following impact. I was in Massachusetts until 1972 when I moved to Palo Alto, and so did Silicon Valley. Because of this, my theory is this could be annoying to at least 7 people in this audience. Because of this attachment to Grosh's law, the East Coast proceeded to build bigger and bigger computers, whereas out on the West Coast, there's 3Com right there, we were, we were building smaller and smaller computers. And who won? He won. So Root won. By the way, I haven't figured out whether this picture is they're putting the sign up or they're taking it down. So while this was going on, I had a company to run, and I was selling Ethernets. And my customers were unhappy because they didn't have very many PCs. And we started selling 3-node starter kits, and they were equally unuseful. So the customers would say, this 3-node network or 2-node network does exactly what you said, except it's not useful. So I made this slide. I went over to Stanford one night and used an Alto over there. We didn't have PowerPoint, so I used a Xerox printer to print this out, and then I took a picture with a 35mm camera, and then I made 6 copies of the slide and inserted them manually into the 6 carousels of my Salesforce. And it basically said, the reason, dear customer, that your network is not useful is that it's not big enough. And what's the remedy to that? Buy more of our products. And they did. And we went public shortly thereafter. This is Gordon Moore chiding me. That slide that I just showed you, this slide, in 1995, a man named George Gilder called this Metcalfe's law. And as soon as he did that, this is one of my hobbies, is defending this law, that the value of a network grows as the square of the number of attachments or people using it. Excuse me. Here's Gordon pointing to me and saying, Bob, Moore's law has been numerically accurate since 1965, and your law has never been evaluated numerically. And so he won that. And there is Metcalfe's law right over there. The value of a network grows approximately as the square of the number of attachments or users. And he was unimpressed. This is Marty Cooper's law, showing the number of conversations you could sustain per area going back to 1900. And you'll notice it's a pretty awesome line. He has lots of data supporting that theory. So we have the internet. It has overwhelmed us with connectivity, and more is coming. We're going now from the megabit internet to the gigabit internet. It's happening now. So if you were overwhelmed by connectivity to date, look out, because here comes a bunch more. But connectivity is not only internet connectivity. So for example, just mentioned radios. Here's a radio that doesn't go shorter distances. Are you all familiar with the Voyager? It's out of the solar system now in interstellar space, but it's still sending radio packets back to Earth, reporting various measurements. And I want to report that it used Manchester encoding in 1977 when it was launched. And of course, the plutonium-powered radio is losing its oomph, and they're down to 160 bits per second. And another kind of connectivity is found in one of my favorite paradoxes, the neuron transistor connectivity paradox. So here's another kind of connectivity. The neuron is this old thing, and the transistor is this new thing, but the neuron outcomputes it. How can that be? Transistors are 1,000 times smaller and 1,000,000 times faster than neurons, and yet brains are smarter than computers. Why is that? And the answer is, my standard answer, connectivity. So here is so CPT-4 is said, it's reported, not confirmed, 1.76 trillion parameters. A parameter is a connection, a synapse, if you will. And it's alleged that the CPTs are next going to go to 100 trillion connections. So I caught Greg Brockman on the stage 2 days ago. He's the president of OpenAI. And I said, are you going to have 100 trillion connections in the next CPT? And he said, we'll see. And then I said, well, even if you have 100 trillion connections, that's not nearly enough to get you AGI. Because the human brain has 10 to the 15th connections, and 100 trillion is only 10 to the 14th. So you're way far from AGI. And he walked calmly off the stage. This is a connectivity issue. Neural networks has the word network in it. Have you noticed? And here's a silly diagram. You know, a neuron and a transistor, except this is 1,000 times bigger than this. And this guy has 10 to the 4th connections, and this guy has 1 or 2. This diagram is highly misleading. So COVID arrived in, you may remember, in 2019. And it was almost as if we built the internet for COVID. Zoom rose to the occasion, and all those professors who said they could never teach a course with video were teaching courses with video. Every course at the University of Texas is available on video, and it pretty much worked. And what we're living now is that we not only did we get a taste of pandemic, we got a taste of collaboration video here. And this is now playing out. WeWork went bankrupt today or yesterday. And that's the real estate playing out. How many people are going to go to the office? How many are going to stay home? So I've decided to repurpose the acronym COVID, and COVID is short for collaborative video. And thank you very much for that. I'm hoping to get some questions.
This isn't a connectivity question, but it's more of a finance question. But I remember back when 3Com purchased an interest in Palm. And I think at the time Palm stock, or shortly thereafter, Palm stock was selling at an order of magnitude more than 3Com stock was. And 3Com already owned 10% of it or something like that. I was wondering if you might have a reflection on that arbitrage opportunity.
You're not entirely accurate, but roughly speaking, yes. Well, first of all, 3Com bought Palm accidentally. We bought a company called US Robotics, and Palm was a subdivision of a subdivision of a subdivision of US Robotics, so we ended up with Palm. And then, as you've reported, the market discovered Palm, and Palm became worth more than, not an order of magnitude, but more than 3Com. So that was a definite arbitrage opportunity, which I couldn't figure out. But eventually, 3Com spun Palm out, so it had a separate stock. And of course, the market cap of 3Com plummeted the next day, not an order of magnitude, but enough to compensate for the departure of this company. I'm not a finance expert because I couldn't figure out the arbitrage. Yes, please.
What do you think of the down? I mean, I've got enough experience with Zoom, as many people have, to feel like it's not great in some respects, especially when government are in control of it, and they can mute you, or they can control the settings so that you don't know who your neighbors are at a community meeting. Just as one example, what do you think are some of the downsides of the Zoom enterprise, and how might they be corrected or addressed?
Well, keep in mind that technology doesn't stand still. So we have Zoom as it is, but we also have Microsoft's version and Google's version, and there's many competing versions, and they're not standing still. They're adding features every day, and so you have to be a little bit careful not to evaluate the idea of COVID, collaborative video, based on the current products. I have not gotten tangled up in government intervention in Zoom. I have not experienced that, so I can't answer that part of the question. I think it's true that let's use the word hybrid and applied to workplace. I think we are entered a hybrid world where some combination of in-person and remote are optimal. And it might vary for person, and who knows. So we're busily figuring that out. WeWork figured it out day before yesterday, sadly. So I think the innovation level in this category is going to continue to be high, and whatever bugs that you're detecting today will probably get fixed. But I don't know about the government taking it over. I haven't heard about that yet. Yes, sir.
You're a legend. Thank you. You've had a lot of careers. What's your next career? I think you count 6 or 7 at this point.
I've begun my 6th career with Professor Edelman in computational engineering here in CSAIL. And my goal is to code again. And what I want to code are models of complex systems like geothermal wells, for example, to try to solve important problems through computational engineering. That's my new career. It's my 6th career. And it's not easy. Ron?
Great talk. I wanted to ask you, I guess that relates to the last question a little bit. If you had a time machine and would go back in your life and do things differently, how would you do them differently? For example, people say that security should have been designed into the internet at an early stage and it wasn't, or things like this. I mean, I don't know if you've reflected on this, but how would you do things differently?
My life has worked out so well that I am reluctant to go back into the past and change anything, because you never know how it would play out. So let's leave it in. But I'm one of those people who identified the security lapse. You know, all those packets we generated have source fields. And those source fields are a great opportunity for various forms of checking. Why is this packet coming from that direction? I don't know. And that opportunity, I carefully put numbers into those source fields, and no one paid any attention to them. So I felt neglected. The other thing is at the Ethernet, the network is divided quite productively into 7 layers. And Ethernet is layers, the 2 bottom layers. And we used to say, security is not our job. Security is up the stack, and we hope you guys take care of it. We hope you guys you did take care of it, yeah. Yeah, so security. The other thing that was missing was economics. Since the internet was built by grad students for whom everything is free, there was no attention paid to how economics would be conducted on the internet. That was now that's perhaps related to security in some way. Yes, sir.
So let's say you're going to go back in time to when you just finished the Ethernet. And given your mindset at that time, let's say we would give you a 2 or 3 hour presentation on the state of the world as it is today. What would have surprised you the most? What would have surprised you the least?
Well, the World Wide Web would have surprised me the most, especially based on the scale of the thing. And we didn't have the World Wide Web at Xerox PARC, for example. There was a blind spot, perhaps. And what would have... That's almost a double negative. It surprised me the least.
Or how surprised would you have been? I mean, we're sitting here building technology, and it's my experience it's very difficult for people who are building technology to project the consequences of that technology over time. How good do you think you would have been at that?
Well, there are resilient strategies that are, even though you don't know what the future is like, you can build strategies that are resistant to many of the bad consequences. And one of those is that the Ethernet had a build it and they will come mentality. The goal was to build the network as fast as possible given the existing semiconductors. So 2.94 megabits per second, kind of a weird number, but it was the only thing we could fit on that little card. The next version was 10 megabits per second, thanks to a chip from Intel. And then we went to 100, and then a giga, and now the current Ethernet is being standardized at 800 gigabits per second. So that is a resilient strategy. build more bandwidth than anyone wants to use, and then that creates more tolerance of different apps that might come, like the World Wide Web surprised us in 1989. But the internet was ready for it. And the internet was ready for COVID in 2019 because, I believe in part, because of that resilient strategy, which is to overbuild.
The internet was not designed to send video. Is there something that it was designed to send? And if it had been designed for video, what might have been done differently?
It was designed to carry ASCII characters. And the principal requirement, I remember we were sending ASCII characters across the country. And there was a thing there called echoplex, where you would hit A, and then A would be sent to the app, and the app would do whatever it was going to do and send back an echo, typically A, but maybe not A. So you had a round trip. And so the requirement was you must carry ASCII characters across the country and back in under half a second. So that's a specific answer to your question. We had parties when we could do that. It was built, oh yeah, I mentioned it was a 50 kilobit per second internet. So if you were serious about carrying video, you would have put much faster circuits there. You would have, instead of going with T1, 50 kilobits and then T1 and then others, you would have been much higher bandwidth, which is where we are now thanks to optical fibers. Optical fibers, which came in the mid-90s, by the way, they came from Bell Labs, which is part of the monopoly that I disparaged moments ago. But thank goodness that the optical fibers came in mid-90s, because that made a video possible. And I could talk to my mom when I called her. I didn't have to hang up after 3 calls. Sir.
So Bob, I want to ask maybe the flip side of Ron's question. You kind of, which is really about whether there are things that you think you and the people around you did uniquely right that maybe we should learn from. Because you kind of, I think, confidently and optimistically said we'll figure out all these problems in the future, which I agree with, because otherwise it's too depressing. But what are the things that you think you learned that you really just got right that we should think about?
We use an American science and R&D system to make the installation of the internet. We overbuilt the plumbing with some blind belief that someday we would need more of it. We used Silicon Valley entrepreneurship to build the internet. IBM and AT&T did not build the internet. It was the likes of Cisco and 3Com and Apple and Intel and startups in the Silicon Valley mode. They didn't have to be in Silicon Valley, but that mode, venture capital, startups, IPOs, all that rigmarole that we go through. And it worked. It built the internet. Vint Cerf was born. Huge plus. So Vint Cerf was who's about to turn 80. Good friend. And I'm serious. His existence had a lot to do with the success of the internet and in espousing basic principles, wanting to reach everybody, for example. So constantly pushing to increase the digital footprint of the internet. And let's see. I'll have to think about some more and talk to you later. Yes, sir.
Mike Dertouzos always used to ask all the distinguished lecturers to distill the experience of their life into some tiny wisdom that can be imparted to students. Your turn.
I knew Mike Dertouzos. He was my boss for a year here. He was the head of I've worked for this lab in 3 different names. It was Project Mac, and then it was LCS, and now it's CSAIL. And Mike was the head during the LCS phase, and he encouraged me to start a company. By the way, he encouraged me to come because he had token ring people in the laboratory for computer science, and we needed to stamp that out. And so I came for a year to try to stamp that out, and I failed. IBM eventually introduced token ring products, which I had to put up with for 20 years. All right, so learn how to sell. The key to selling, while you're here, listening. That's a distillation. I wish I had learned how to sell sooner than I did. I ended up learning how to sell when my company needed it most. So you talk about bad decisions with good outcomes. They made me head of sales and marketing. Bad decision. Good outcome? Yes, $1 million a month. We went public on that basis. So occasionally bad decisions do lead to good outcomes. And the IBM gave me 2 shots, Franklin Lakes, New Jersey, and Research Triangle Park, North Carolina, to go into rooms full of engineers who explain how Ethernet worked. I was 6 years ahead of them. They had never built a local area network before. So I slaughtered them. I won the argument, as we say in the sales trade. What I didn't get was the order. So in selling, you can win the argument, but not get the order. And I did that. I didn't know what their considerations were. I didn't know who the decision makers were. I didn't know what alternatives they were facing. I did none of the basic sales research, and I went in and won the argument. Every time they had a fact, I had a better fact. So I wish I had learned a little bit more about selling prior to those 2 events, because that would have saved, as I mentioned before, 20 years of putting up with that stuff.
Yours was supposed to be the last question that you So I have 2 questions about standards. The first one is really easy. Why did Ethernet and all the layers 2 stuff go with these standards instead of the Internet standards? The RFCs that were.
So we got Digital Equipment Corporation and Intel Corporation to agree to want to network their products. And we started meeting to make a standard for connecting between those 2 companies. But the lawyers wouldn't let us meet anymore because DEC and Xerox and Intel could be meeting in restraint of trade. So the only way we could continue meeting was to dedicate ourselves to an open standard. So then we launched an effort in the fall of '79 to design the standards process properly, because it can run amok. And Hewlett-Packard which is in Palo Alto, so it's the geography is a little important too. So there is HP across town, and they had just finished making a standard for their instrumentation bus. HPIB became IEEE 488. And one of us knew Don Lockery, who had made that standard. You see, it's personal. Called Don and said, we want to make a standard. You know how to do that. What should we do? And he says, first you make an IEEE project, you give it a number, you start scheduling meetings. We had our first meeting at the Jack Tar Hotel in San Francisco in February 1980.
So if you called in, it would be an Internet standard.
It would be an IETF.
But there was no RFC.
But there were RFCs around that time, because RFC 1 was from 1969, so the process was there. And I asked because now to be in this IEEE standards process costs a lot of money, versus the Internet process is completely free.
It's funny, I don't really have a good model about all that. I think the IEEE 802 process has been working wonderfully for 40 years. And I was unaware that IETF did hardware standards. I thought they only did protocol standards. You know, like Wi-Fi, for example, is an IEEE standard. So I think that was a division of labor, but I don't remember who said, okay, IEEE, you handle hardware, and IETF, you handle, so I don't remember that meeting. It must have occurred, though. So, but we got Don Lockery, may he rest in peace, to just do what he did for 488, to do it for 802. And it not perfect, but it worked.
We're going to take two more questions. Charles, second to last question.
So Bob, you're famous for your people skills, although some would characterize them one way and others would characterize them another. What kind of advice would you give to students about the important people skills to have if you're a MIT student?
Well, I've already revealed my first answer to that, is listening and selling. Listening is a recurring plus. So, and by the way, to listen, you need to stop talking. In case you wanted a tip as to what to do. It pays for you to like people. This is, sharpen your question, it means entrepreneurial success?
Or generally, what should MIT students for having a bright future? So it could be entrepreneurial, it could be whatever they're...
Well, you want to be good at something. And to be good at something, it has to be fun. If it's not fun, you will not be good at it. And then and it's important, it's better if you were good at something valuable. I'm in Austin, Texas, and there's a lot of people who know how to play the guitar in Austin, Texas. But the rule in Texas is if you get a gig playing guitar, there's 15 people in the audience who are better than you are. So guitar is not one of those valuable skills you should learn. I don't know. It helps to like people. I actually started liking people in the middle of this process, and then it proved very valuable. Well, MIT is full of excellence, and associated with that is judgment and you know, disparaging Harvard, which is one of my hobbies. And that's not productive. It is productive to like people and to be interested in what they're doing and to get out and socialize. And then when you need people in forming various networks like entrepreneurial networks, you know about them. I once threw a party in Woodside, California to recruit people for my company. And my next door neighbor was Joan Baez. And she walked into the party. My parties became famous thereafter. I threw parties that Joan Baez went to. And by the way, I've told this story in this very room before, to be faced by an audience full of people who never heard of Joan Baez. But it helps to like people and to build your networks around them. One more.
So Bob, last question. Also advice for all the young students who aspire to get a Turing Award?
What took them so long?
I'm an extremely unlikely winner of the Turing Award. Here's my analysis. Computer scientists, there's two kinds. Mathematicians and engineers. And then of those, there's two kinds, researchers and entrepreneurs. And so I'm a engineering entrepreneur, which is the least populated quadrant for the Turing Award. So that's why it took so long, 50 years. I'm extremely grateful for it. Did you know that that prize comes with $1 million in cash? 1, 000, 000, period, 00. Did you know that? Oh, God. So I've already made my first donation. I donated $100,000 to the National Academy of Engineering. So that's a model of what I'm planning to do with the money. But I can do anything I want with the money. I could buy beer with that money if I want.
Is it taxable?
It is taxed, yes, that's right. First thing I checked. I also checked, I got the award. You got your award too, on a Saturday night. So I lost the interest on Sunday. Thank you very much.
Ladies and gentlemen, Bob Metcalfe.
Thank you.